Today, I'm proud to present to you this panel of experts highlighting the many useful ways that 3D scans can be utilized, as well as the tools available for working with that captured mesh data. You're going to get a nice overview of what's possible with 3D scan data, starting with the scanners and then moving into software options, applications, and practical advice on how to best utilize these tools to get your job done faster and better than ever. So as I mentioned, we have a panel. We have 4 presenters today. First up is Ian Sayers. Ian is our 3D scanning product manager here at Hawk Ridge Systems. Ian leads our 3D scanning operations and services, spending much of his time helping companies choose and implement 3D scanning systems and related tools. Before coming to Hawk Ridge, Ian worked as a 3D printer repair technician and CAD application engineer before transitioning into 3D scanning back in 2014. His hobbies include blacksmithing and Mayan epigraphy, which I had to Google to learn that it's the study of ancient inscriptions and epigraphs, like, for example, maybe the Rosetta Stone. Ian's going to be summarizing the scanning hardware available today and where it best fits into a wide range of applications. And then we'll have Jeff Moody, an application engineer with 3D Systems who started his career in the software industry as first a biomedical designer using freeform and haptic devices to make surgical guides and medical devices for the healthcare division of 3D Systems. 2 years later, he transitioned into an application engineering position and became the sensation that you will see today. Jeff will be demonstrating how digital clay modeling can be the perfect solution for creating freeform shapes and using scan data to design around organic geometry like the human body. Then we'll have Matt Fisher, our 3D scanning application engineer here at Hawk Ridge, and he specializes in 3D scanning and reverse engineering. He's got a degree in mechanical engineering and used his knowledge for rapid prototyping and machine design before getting into creating high quality detailed meshes for reverse engineering, as well as quality control tools used with metrology grade scanners like the hexagon line. Outside of work, Matt enjoys heritage preservation and gets to scan statues and landmarks, capturing that history. Today, Matt's going to show you how scan data works in inspection and quality assurance applications. You'll see how to quickly inspect parts in a variety of ways, how to implement an automated pass-fail process, and he'll touch on the merits of various hardware like CMMs, portable arms, scanners, lasers, as it relates to quality assurance. And finally, Sean Parker, he's the regional manager for software at 3D Systems on the West Coast. He joined 3D Systems back in 2012 as an application engineer and spent time training, providing technical support, as well as working with the marketing and sales teams. He's a degreed mechanical engineer and gained industry experience as an aerospace machinist. Today, he's going to share the basic principles of reverse engineering from scan data, whether that's prismatic or challenging organic parts. He'll show you how to quickly create reference models, as well as fully editable parametric models with a full feature history, and some techniques for copying parts exactly, implementing changes, and designing around existing objects, and ensuring all that's accurate. So up first, we have Ian.
Hey guys, thanks for joining us. So I'm going to talk about just some hardware basics. We don't have enough time to do a real deep dive. We're going to do about 15 minutes each, and then we'll have that Q&A at the end. I'll stick around until all the questions are answered. And if anyone is interested, I'll also be firing up the webcam and a 3D scanner, and we can go through some stuff live and touch on your individual areas of interest if you're interested in that. So I'm going to talk first about the various types of hardware that are out there. So if you've been looking at scanners, you probably noticed that there's a lot of them. So I'll try to simplify this and break them down into a few distinct categories and discuss where they fit in best and what are some of the pros and cons. I can really only scratch the surface here, but like you saw right here, we'll be doing some upcoming deep dives on all of these individual topics that we're talking about today. The dates aren't all set, but the hardware one is going to happen on May 21st. So if you want to go down the rabbit hole with me, you can join me next month there. So lots of different types of scanners. And the first type I'll touch on are handheld scanners. So these are really versatile scanners, and that's in large part because they leverage a great tool for the job that you already have, which is a human wrist. So they typically cost a little more than a comparable tripod-mounted system, but they tend to be a lot faster and more versatile. Like I said, partly that's the human wrist. Just imagine that you had to spray paint something, but the spray can was mounted to a tripod and you couldn't move it around. It'd take you a while to paint something, wouldn't it? So something with complex geometry is going to go a lot faster with a handheld scanner. And obviously just the portability and mobility, the ability to reach in behind stuff is going to help you get into a lot of hard to reach places and stuff. So all that adds to the versatility. Handhelds typically lose some accuracy over distance. So if you're shopping for these, you're going to see two accuracy ratings, just a given accuracy on any given measurement, and then accuracy over distance. A lot of times there are additional systems like laser trackers or photogrammetry systems that can augment these type of systems to hold better accuracy on really big objects. Handheld only refers to the form factor, not the technology type. So handheld scanners can be structured light, they can use lasers, and some use both. Like this one up top here, that uses, here, let me use a laser pointer. Woo, there we go. So this one here uses structured light and an infrared laser, even though we primarily consider this a structured light scanner. So structured light works by projecting a pattern onto something and measuring the distortion. So just like this innovative bike light you see on the left here, it projects a grid down, and because that grid is distorted, it's easy to see that there's a bump coming up there. And that's exactly what structured light systems are doing, just in a more sophisticated way. They might use a more complex pattern like you see projected onto this nice lady. There's some other stuff going on behind the scenes, but this pattern distortion is the primary mechanism behind structured light scanning. Now, because they work by projecting a light pattern, they may have some trouble in direct sunlight because they're going to be competing with that, right? It's going to wash out the pattern. They might have more trouble with scanning shiny, polished surface than lasers do. We'll talk about that in a few minutes. On the other hand, they can sometimes be higher resolution than lasers. They tend to be more affordable than lasers in general. And they're often faster and have bigger capture areas. And a lot of them can capture full color, like we see here. So a lot of these structured light scanners do not require the use of stickers or targets. So maybe you've seen in the past scanners where you have to cover the object with stickers like about 4 inches apart. So you want to scan a car, you're talking about 500 to 1,000 stickers or something. So these don't use those. That's one thing that makes them great for color applications. And if you want to, these colors you see here, these are straight out of the scanner, but if you want to take these into a rendering program and touch them up, you can get very photorealistic results like you see with this scan. This is from a scanner called an Artec Space Spider. It is a structured light scanner. The Artec scanners are among those that do not need targets to use. So that makes them especially good at things that have a lot of texture like this, where you don't want to cover up texture. And of course, the high resolution lends itself well to things like meshes and the textures of fabrics. You also have those same things in, say, museology and artifacts, where you're not going to be allowed to just put stickers all over something. And of course, again, the high resolution comes into play. So those are some of the pros and cons of structured light. Then the second general type of scanners you see are laser scanners that use triangulation. So this is where we place a camera and a laser separated from each other at an angle so that they point down at a central focal point and form a triangle like you see here. And so you can imagine here this target surface, if we were to move this up toward them, then this laser line is going to appear further to the left in the camera's field of view. And if we move it down, it's going to appear further to the right. So based on where this dot or line appears in the camera's point of view, we can tell the distance to the target. And that's more or less how these work. These exist in handheld form. Those are the ones I alluded to that you have to put stickers all over stuff. But a more common form factor that you see for this type of laser is attached to an arm like you see here. So the arm has encoders that record its position with really high accuracy, and that maps all the data together. So you don't need any targets. And this makes them a really good choice for a lot of applications like scanning thin parts like sheet metal, and the touch probe can trace outlines and cutouts instead of you having to try to scan those really thin edges. And it can also capture areas not outwardly visible with the probe. It can collect measurements on the fly with the probe, rather than processing scan data and taking measurements off that. So these are a longtime favorite in quality assurance. This type of laser tends to be the best type of laser out there for hard to scan surfaces like chrome. And they tend to get deeper into things like cylinders and pockets than structured light can. So like I said, they can be a dot or a beam. In this case, this is a stripe. This is a stripe, kind of like you'd see on a supermarket scanner. And it is a blue laser in this case. The third major category are scanners that use the known speed of light to judge the distance to a target, and this includes LiDAR scanners. So you've probably all seen one of these laser tape measures in the hardware store, and this is a rudimentary LiDAR system. The difference between this and a LiDAR scanner is that the LiDAR scanner, where it emits the laser, it's going to be able to spin on multiple axes. So this lens spins around this way, and this whole head spins around, and it can shoot out this big dome of laser beams, right? So we have an encoder in both of those spinning objects, and the encoder records the angle that each one was shot from. And because the speed of light tells us the length of the line, the distance, those two pieces of information give us the coordinate of each of these points relative to each other, and that allows us to create a cloud of points, appropriately called a point cloud. So the long range and accuracy over big distances makes LiDAR scanners a really good choice for scanning big objects, entire sites. This is great if you wanted to scan a factory to plan a new conveyor install or some kind of retrofit, or if you wanted to scan a mine to navigate a piece of machinery through it, or a complex piping layout that goes from one side of a factory to another, an archaeological site, you get the idea. So in fact, I believe that LiDAR scans from a popular video game have been indispensable in the restoration efforts at Notre Dame since the fire, so that's interesting. Another related tech is a laser tracker. So instead of firing out a bunch of points, these tend to fire a single beam out. And these are even more accurate over long distances than LiDAR. And these can be used like a giant coordinate measuring machine, where you can walk from one end of the building to another and touch off points and know the distance between them really accurately. So if you wanted to measure, between two pipe flanges across long distances or something, these could be really good. And these can work together with handheld systems. So for instance, you can use this handheld scanner. It's got these little nubs on it, which have these little tracker dots. And the tracker is constantly following these and just tracking its position. And so you have the benefits of the handheld, where you're able to get up close and reach your arm into things. But it's constantly being mapped onto the larger coordinate system provided by the laser tracker, so you have much better accuracy over distance. Another way for scanners to work together is less direct. Even if scanners aren't communicating together directly in real time, you can often combine data from two scanners for the best of both worlds. So for instance, here we have Matt Fisher, who's going to be presenting in a little bit, and he's deep down in a lava tube in Washington State with a LiDAR scanner. And here's a scan of Matt done with an Artec Ava, a popular handheld. In fact, the most popular handheld. So if we just wanted to merge two scans together just to give something a sense of scale, or again, the example of wanting to navigate a piece of machinery through a salt mine or something like that, get a conveyor through your factory, you can combine data from multiple scanners, put two objects in the same scene. In this case, we do it for a sense of scale. You can see Matt at the very end down of this big old lava tube that is miles long. Another more direct example would be like this, where we have a single monolithic object, not two objects. And there's a specific area of interest where we want more detail on. So we've scanned it with one handheld, and then we've taken a higher res handheld and scanned a certain area of interest, and we've replaced the previous data so that, again, we have the best of both worlds. So that's enough about hardware for now. If you want to go into more hardware with me, you can join us on the 21st, like I said, and we'll go down that rabbit hole. For now, I still have a few minutes, so I'll cover just a few kind of preemptive FAQs. Yeah.
Hey, Ian, there's a great question in the question pane by Thomas.
Sure.
Could you compare the various scanning technologies and their abilities to scan tough stuff? Translucent objects, reflective surfaces, and then surfaces with oblique or sharp angles as it relates to the optical axis.
Sure, absolutely. The oblique or sharp angles is really just a question of resolution for the most part. I'm going to talk about resolution here in a second, and I picked out 3 of the very most common FAQs to cover for the rest of my time, and one of those has to do with scanning shiny objects. So let me just breeze through those real quick. So talking about resolution, this is more of a misconception than an FAQ, really. Something I hear a lot. I hear this even from really experienced engineers all the time, because these just aren't concepts that we play with in most of the engineering world. And so I'll hear something along the lines of, well, we have really high accuracy needs, and we're looking at this scanner because we saw on the brochure that this scanner has 0.1 millimeter resolution, which ought to meet our needs. So if you work with scanners, you've already spotted the problem with that statement. But again, I hear this all the time, and the misconception here is that resolution and accuracy are directly related, which they're not. Resolution isn't about how accurate the location of a point is. It's only about how many points there are within a given area, just like DPI with a photograph. So, the dots on the top one here, they all exist in the bottom one. And there is no reason for us to think that the location of these dots are any more accurate between these scans. They might be, it would depend on the scanner, but there's no reason to assume that. But if we go in and scan this with a higher resolution scanner and get a bunch of dots between all those points, we see that we were missing a lot. So, here's more of a real world example where we have these little vents and stuff, and it hasn't really been properly expressed. So there is sort of an indirect relationship between accuracy and resolution, just in that you need high resolution in order to accurately express detailed shapes, but that has nothing to do with dimensional accuracy, right? So I kind of like to call that like detail fidelity or something, so it doesn't get confused with dimensional accuracy. But down here where there's not a lot of detail, the battery pack, if we wanted to measure between two sides, one of these scans might be just as good as the other. You don't really need higher resolution for that. So that brings us to one of his questions about hard to scan surfaces. This is probably the most frequently asked question. People find out early on that this is an issue for most scanners. It's very true. The only technology that's largely immune to this is going to be X-ray and CT scanning. And those are big, full bathroom sized affairs, big, heavy, expensive things. Only the biggest companies have them. So this is an issue that 99% of us are going to deal with at some point in scanning. Some scanners are better than others, like I mentioned earlier, and lasers tend to work better than structured light in this regard. and some lasers work better than others. So that arm-mounted laser that we saw earlier, the one the guy was scanning the Red Bull car with, that's probably the best one out there that I've seen. That one can just slay polished chrome. It can even scan glass to some extent, which is just crazy. These are not in everyone's price range, and they're not going to be the ideal scanner for everyone's use case. So a lot of us are, who don't have one of these RS6 lasers from Hexagon, are going to be using some kind of doling agent. So, one option could be a talc spray. This is just something that welders use on a daily basis called developer spray. And it's just talc in a can, basically, and it wipes away clean. Or you could use something like this disappearing spray. If it's something like a fabric or something that you're kind of worried about putting talc on, you could use this. And this doesn't use any pigments or particles. It just goes on opaque and it all evaporates. You can see it here on this phone halfway through the process of evaporating. So yeah, shininess and capturing thin edges and stuff is something we'll dive into a lot more on the 21st, but that's the gist of it, is that you need a very high resolution scanner to capture thin edges, and lasers are going to work better for capturing thin edges. There are some tips and tricks that we'll go over for capturing thin edges with other technologies like structured light. A simple one would just be throw some masking tape on the edge, and there's your edge location. Double up a piece of tape and subtract half of that with your calipers. So there are workarounds, but yeah, in general, lasers are best for thin edges, and they're also best for shiny stuff. And blue lasers specifically are the best all around. Otherwise, you're going to be using talc. There's not much out there that scans chrome. A tie for the most frequently asked question is about combining scans, and it usually goes something along the lines of, if I have a part sitting on a table and I scan it, how do I scan the bottom? So the answer is deleting the base and combining scans. So, pretty much all scanner interfaces have a way of deleting a base plane, or some kind of clipping plane. And they generally all have a way of combining scans. So here are two scans. One I only scan from the top. One I have a scan from the side. There's some geometry that I need there. So scans are basically like 3D panoramas. So just like with a 2D panorama, it works by, you need some overlap between each photo, and that way you can find some common features of them and say, hey, the fork in this tree branch in this picture is the same as this one in this picture. And you do the same thing with 3D scans. You go, this is here, this is here, this is here. There are also automated ones, but a lot of times you need to take manual control like this. You get it close, and then the computer does the rest for you and does a really fine alignment on it.
Hey, Ian.
Yeah.
This is Tim again. We've got one more question, but then we probably better move on to Jeff, because we're almost coming up on a half an hour into the webinar. But I wanted to have you answer this last question as well as you could in just like a minute or so. But Ivan asks, how well do handheld scanners capture hole centers and sizes? This could be a threaded hole as well.
It is all over the place, and lasers are going to be the best for capturing holes. And this has partly to do with an exposure effect that we find in photography as well. I'll talk about that a lot more in May. But basically, lasers are the best. And you want pretty high resolution. There are other tips and tricks like putting talc in a hole, but not on surrounding surfaces. The very best solution for hole locations is going to be one of those arms that you saw, because you can simply nest that circular probe into a small hole, or you can trace a big hole with the probe, and that is a very quick, very accurate way of measuring hole locations. There's really nothing that beats it. Awesome. So a few final words just about scan data. Scanners output mesh and point cloud formats. a lot of workflows or softwares are going to require you to convert the point cloud into a mesh. Most garden variety CADs are going to need a mesh. And in general, that is the preferred format. The most common format is an STL. You know, most things that output point clouds have the ability to turn them into meshes as a general rule. The file types that they output, sometimes there are some proprietary formats, but generally they are universal. That's the nature of this industry, is that any scanner will work with any industry standard inspection software or reverse engineering software and vice versa. So it's not something you need to worry about a lot. And as far as traditional scans go, there are, most CADs can input an STL, and sometimes a few other mesh formats like SolidWorks can also open OBJ. That said, most traditional CADs are pretty limited in their capabilities with it. So I kind of view this like a multi-tool where, you know, if you broke down in the middle of the desert, you would be really happy to have your Leatherman tool on you, but you're sure not going to use your Leatherman tool to rebuild your engine back at the shop. So that said, let's go ahead and move on and take a look at some of the tools that we would use, like Freeform or Geomagic Design X. So I believe Jeff Moody was up next. So we'll go ahead and turn it over to Jeff.
Hello, everyone. So I'm going to go ahead and share my screen. I'm going to change to presenter. There we go.
We got you.
Okay, perfect. So I'm going to start off by explaining a little bit of the UI of the software and some of the key differences between Freeform and other CAD packages. To start, Freeform is a really good organic modeler. So anything that you can't do in SolidWorks or NX or Creo, you can do in Freeform. Think of if you need to create braces for a hand, or if you need to create orthotics and prosthetics, you can do that in here in a very streamlined and efficient method. Also, I pair this software with a piece of hardware called a haptic device. And if I pull up Google really quick, this is the Touch X. Basically, I hold my hand just the way this person is holding it. It's kind of like a pin with a button on it, and each one of these joints here has an encoder that when I'm touching the model, it pushes back against my hand. So when I import a model here, I'll go ahead and select the head. I will be able to feel all of the contours of this person. So if I come out here and I pick my I pick a carving tool, I can actually feel the contours of this person's forehead, her eyes and her ears and things like that. So again, quickly to talk about the UI, over on the left-hand side is all of our tool palettes. They can be scrolled up and down here, and they're kind of color coordinated. So as Ian was saying, this is a STL. This is a polygonal mesh. If I right-click over here in the object list, and I convert it to a voxel clay, that's now a different unique geometry to Freeform. Basically, it fills the inside and the outside full of data and allows me to do different things. So if I was using my carving tool and I cut a hole in a STL, it would just create a hole. If I cut a hole here, it creates kind of a cave. So you can think of this as digital clay. And because it's digital clay, I can change the clay coarseness, or I can change the density of the clay. I can tell my software that I want this to be the consistency of Play-Doh, or I want it to be the consistency of designer's clay. So my object today is going to be creating a mask for a pandemic, let's say. And the way that I'm going to do that, I'm going to draw a few curves on this organic model here, and then I'm going to use those curves to create a surface. Once I have that surface, I'm going to go ahead and convert that to clay also, and then I'm going to probably put a stamp on it, or maybe put some things to affix straps. So I'm going to go ahead and start by coming up in my tool palette. Under the curves tool palette, I'm going to select the draw curve option, and down here is a Dynabar. And you can think of this as just the tool attributes. So anytime I pick a different tool, it's going to give me a different set of attributes that are only pertaining to that tool. So again, I'm going to come up to the bridge of the nose. Down in the Dynabar, I'm going to fit to clay. And then I'm just going to put points down. So this is very, very similar to a 3D spline, but since I have it fit to clay, it allows me to do a little bit, it allows me to just fit to this model. And I'll hit E to end. And now I have a rough outline of my mask. If I wanted to modify that, I can again come over to the curves tool palette. I can select the select option, highlight my curve, and then just modify it slightly. And I'll go ahead and do that in a couple of points here. It's pretty good. Maybe push this out. Let's check the bottom just a little bit. There we go. And I'll just check the bridge as well. And maybe move this point down just a little bit. That looks pretty good. Okay, the next thing I need to do is put in a plane because I want to make this a 3D object. So I'm going to press F2 on my keyboard to get a head-on view. Then I'm going to use something called a J-turn, which allows me to go 90 degrees in any direction. And then I'm going to come over to my planes tool palette and select create plane. I'll then orient this view, and then I'll push it back into the global origin. I'll select this little caret down here in the Dynabar, and I'll change my translation to X to 0. This pushes it into the global origin right onto the global planes. So if I press F2 again, you can see that my plane is perfect. Now I'll go ahead and put a couple sketches on here. To do that, I'll select the plane, and then I'll just draw a line. This is going to be the profile of my mask. So again, I'm drawing another line at the chin, and I want to leave enough room so that this person can talk and move their chin freely without having any issues. There we go. Then I'll add a fillet to this sketch. Down here in the Dynabar, I can change it to a specific size. And I'll change that to 20, and then create those. I'll hold Alt-M to shrink my plane down, and then I'll convert this 2D sketch into a 3D sketch by coming up to the Curves palette, selecting the Copy from Sketch option, and then highlighting each thing that I want to turn into a 3D object. Over in my object list here, you can see that I now have a bunch of different curves. I have a plane, and then I have another curve up on top. I'll go ahead and hide my plane, and then I can trim these two together. And the way that I do that is I come over to the Curves tool palette, and I select Split. Then I just need to choose which sketch line I want to split. It'll highlight. I'll click it, and then I can select anywhere on this spline. I'll select it right at the intersection here, and then I'll do the same for this spline as well. I'll do the same thing on the bottom. Right there. And there we go. This one on the top might have been too far off, so I might have to modify it. I'll go ahead and use the select tool again, highlight the pigtails, and then just delete them. There we go, and it looks like, yeah, those two need to be connected together. So I'm gonna go ahead and take this endpoint here, and then just attach it to that one. All right, so I need to have, for this to make a nice, model, I need to connect these lines together. To do that, I'm gonna select Join, and then highlight all the lines that I want to join together and connect them one by one. And then finally, I'm gonna split this edge here. Again, selecting Split, highlight this area here, highlight this bottom area here, and now I have 4 different sketches or 4 different curves. At this point, I can scroll down in my tool palettes, come down to the patches, and then create a patch. So this patch doesn't really work right now, right? We kind of have an issue. It's kind of sticking through the face, so I need to modify it. And the best way to modify this patch is come over to the Patches tool palette and select Shape Patch. I can highlight the patch. Then down in the Dynabar, it says Section Step. And really all I need to do is draw lines on this patch. So I'll draw one here and I'll draw one here. Then I'll go to the next step in the Dynabar, and I'll just pull these out. So here's my node, and I'll just pull it out. And I'll do the same thing to the bottom one as well. And it's still giving me a little tangency issue, so I'll use the tangency arrows and continue to pull. And this takes just a second. There we go. And I'll change the front of the mask just a little bit. There we go. That looks pretty good. Maybe we have an issue right here where right under the eye, it's kind of cupping back into the eye, and we don't want that. I can easily step back, make another cross section. Let's see, right about there, and then modify that as well. Let's go ahead and turn this down just a bit. Then I'll open up this area again. There we go. I might need to shrink this back up just a bit. Whoop. Right there is probably good. And then I'll select apply on the Dynabar. Now, once I have this half of my mask, I can go ahead and copy this over to the other side, and then I'll stitch them together and then convert them to clay. So again, to copy it over to the other side, down in my patches tool palette, I can select mirror patch or solids. This software can work in a bunch of different geometry types. So if you're working with SolidWorks, you can directly import solid bodies into here. If you're working with any kind of scanner, you can directly import any kind of STL, OBJ, or PLY, neutral file formats. And if you're working with sub-D surfaces, you can import them as well. So here's my center plane. All I need to do is select my, my patch, and then I'll select apply. At this point, I have 2 patches in my object list, and I'll go ahead and stitch those 2 together to create one patch. So I'll select all and select stitch, and now I have one patch. At this point, I can go ahead and convert this to clay so that I can model it or change it up or do things differently with it. Like here might have produced an issue and I might want to clean that up with clay. So to do that, in my object list, I'm going to right click, select copy to mesh or STL, then say okay. And then finally, I'm going to copy it to clay as well. Oop, this might produce an error for me. We'll find out. Yeah, yep, it is producing an error. Okay, so I will step back 2 steps. Go ahead and delete out my second patch, convert this single patch to clay, and then duplicate it, and then copy it over to the other side. So again, copying this to an STL format, and then finally copying it to clay one more time. This time, I don't want it to be just a solid chunk. I want it to be about 2 millimeters thick. So down in the Dynabar, I'm going to select thicken, and then I'm going to set it by a specific amount, 2 millimeters. And earlier, I was saying that I could set the clay coarseness to either be really malleable or really, really rigid. Here, I'm going to set this to be fairly rigid. I'm going to set it at a 0.15 clay coarseness. And then I'll select apply. And this takes just a second to work. But once it's done, I now have this nice model that I can mirror to the other side. So again, I'm going to move up in my tool palettes. Under construct clay, I'm going to select mirror clay. I need to choose my mirror plane, which is the only plane that I have available. And then I'm going to select mirror entire piece down in the Dynabar. I'll go ahead and select apply. Oops. Control Z. Try that one more time. Mirror piece. Mirror entire piece is a new piece. Preview, apply. And now I have my opposite side. I can then do a Boolean operation, which will join these 2 pieces together. Select OK. Join these 2 together. And once this is done, I'll have a completed mask. Tim, are there any questions so far? Are we still doing good?
Yeah, we're doing well. No questions yet. So if anybody is curious out there, feel free to enter your questions away and we'll get them answered.
Okay. Last but not least, I'm going to go ahead and modify this a little bit because I see that I have a problem here. Go ahead and hide my curves. So I can see that I have kind of a split here, and it's okay. In this software, I can modify and fix this very quickly. And to do that, I'm going to go to Mask, which is going to highlight everything red and prevent me from modifying this at all. Well, once I do that, I can then come up and use my other tools to add clay onto this. So really, this is just creating a structure that won't allow me to modify or mess up my original model, but allows me to add on top of it. So I'm just going to go ahead and add in a little bit of extra clay here and kind of close up this seam. I'm going to hit the bracket key and enlarge my tool just a little bit. Slowly but surely, it kind of fills it in. We'll keep going just a little bit more. And I might drag this outside of the model as well. So I'm going to go ahead and turn off my mask. I'm going to fill this in just a little bit more using the tools up above, the hot wax tool. There we go. Oh, crank my level up just a little bit so I can get a faster result. Let's shrink my tool down. There we go. So here I filled in just that small area, and I'm going to go ahead and defeature it. Actually, that's okay. I'm going to use the tug tool and pull it out from the chin just a little bit. And there we have a custom mask made from an organic shape, made from an organic scan. So I think with that, we can go ahead and turn it over to the next presenter if there's no questions.
Great, thanks, Jeff.
Yep.
So up next, we have Matt Fisher. Matt, I'm going to give you the controls and then you can share away.
Perfect. Let me just, let's see here. All right. So what I wanted to talk about was a couple parts of the, oops, hiding the control panel. So I just want to go over briefly just what is Control X. So Control X is a metrology grade software from Geomagic that involves being able to import in various types of scan data and being able to compare it to your CAD bodies. So this is in the situation where you now have your scan and you want to compare it and see how maybe a machine part compares to what you have engineered. So we are able to do various types of importing in and aligning between these imported data and CAD bodies. We can even go a step further and create our 3D and 2D color maps for inspection. Just adding in control points, if we need to focus on a certain area, we can definitely do that and then add in dimensions afterwards. And then finally, we can generate a report if we need to batch off a couple of different scans. So we scan the same thing 6 times. We can create different types of routines, copy them over so that way it's just very quick and automatic. So jumping into it, just to go over a brief little example of how you would go about doing a comparison, I have a scan of this demo block and the CAD model of it. And I'm just going to go right off the bat and just do my initial alignments. As you can see from the Home tab, we have a couple of different forms of alignments. So not only am I going to do the initial one, but I can now even go further and say, okay, well, let's do a datum alignment. And choosing my different planes that I want to use as my datum points. So maybe like a top plane, a back plane, and then this cylinder. All my degrees are locked, and I can say okay. And then if we needed to go an even further step, I can do a best fit alignment just to make sure I'm using a good amount of my data just to make sure everything is perfectly aligned. And we can kind of get this bleeding effect as you see as I rotate around. That means that we're pretty well aligned. And everything is also stored in my feature tree. So what we can now do from here is if we need to get some measurements, I can insert in different features. So let's say we need to insert in a plane to measure the top and bottom. Well, we can definitely do that. As you can see, we can also insert in cylinders and spheres. And there's different ways to do our extraction. So we can do a 3-point method for something like a plane, just to gather a couple points. We get a little preview and we can click OK on that. And then we want to make the bottom plane. Well, we can go over back into the plane tab. And this time, I'm actually just going to highlight parts of it. And as I further highlight, the preview will start to appear, get a better idea of where this plane needs to fit. And then if I click OK, let's see here. Whoops. There we go. There we go. And now we have this bottom plane. And so with these inserted features, we can start just throwing in some dimensions right on top of them. So we can go from the bottom plane, the top plane to the bottom plane, adding in even a tolerance if needed as well. We get our measurements. And again, building it into the feature tree, we now have this viewed as part of our analysis. We can also insert in different CAD bodies to do our measurements. So we have this sphere right here. Well, I can select on the sphere, again, just define a part of it, and then insert that in. And now we have something that we can start pulling, again, dimensions off of. So if we need to know like a radial dimension of the sphere from the scan data just for a comparison, well, now we have that. But not only can we do 2D measurements, like I said, we can do 3D or regular dimensions, but we can do 3D dimensions in color maps. So I'm just gonna hide in all of my features and this datum alignment. And going over into the compare tab, we have this 3D compare right here. Clicking on that, and then adjusting our sampling ratio if we wanna go further into detail, but we can go to the next arrow and actually get a preview of what our mesh will look like. And I can, as mentioned earlier, if needed, we can select on certain spots that we need to highlight. Maybe we need to display this as whiskers, really customizable. And if we ever need to edit in the future, it's always possible to right in here. And then I can even, just to give a brief example of the 2D measurements, I can select on like a back plane, and now I can adjust the slider. And then go into the next tab, I can say, okay, well, what's this key area right here? What's this key spot right here? Just getting different types of measurements. And again, if I need to adjust my tolerance, perfectly possible right in here too. So let's say, we've created this entire routine. We have our measurements where we want. We have our 3D or datums. But again, we have various types of scan data. Well, what we can do is, like I said, batch this off into different results. So what I'm going to do is duplicate this result, because this is, let's say, our master, our master result that we are going to run this routine on multiple parts. Well, we can duplicate this. And then in our second, we can now go back into import. Actually, let me delete this CAD block. So I'm going to get rid of the current measured data because I'm going to insert in a new one, and import in. Looks like it. There it is. Oops. Here's our second scan data. So I'm just going to import that in. And once we bring it in, we can just rerun this routine using our refresh button. So clicking on this, it's going to go through, rerun all of our alignments, inserting in all of our planes, and then even doing our 2D comparison. So you're going to see this adjust pretty quickly once all of our importing and finishes. And there we have it. So now we have two different routines that we can jump between if we want to see how they compare. And another thing we can even do before we even generate a report is we can add in different custom views. So a lot of times you might need to show this to a customer and they say, well, we need to see what it looks like from the top view or a front view. So I can change my angle to here. And then right here in our navigation tools, I can say, well, let's add a new viewport. So now we have a custom view that we can snap to, add it into our reports. If I change my angle around, that's no problem. I can actually just snap right back to that if I need to make any extra adjustments. So in our generate report tab, we can, just wait for the window to pop up. We have a way to select what entities we want to show in. So let's say we need to really just show our datum alignment. Well, we can get rid of our initial and our best fit and bring them right over into here. As you can see, it's only result 2 showing right now. So even all these spheres and planes, they're gonna pop up, just a little preview showing what they are. But again, if we aren't needed or don't need them in a report, we can bring them right over and then maybe even switch over to our results 1 and say, well, actually, let's bring in our datum alignment from results 1, our 3D comparison, 2D comparison, and if everything looks good and we can add in our titles if needed or get rid of or add in new part numbers, we can definitely do that. So I can say this is like a test part, and then I can click generate, and it's going to go through and create a preview of our report. So again, what's really great about Design X and Control X is that everything that we do is editable. So if we need to adjust something in the future, even a report, all customizable, and we can go back and add them in. So now we have a report preview showing. We can see our different parts, our CAD bodies and our scans. Here's our datum alignment, just showing the accuracy and angle of that, where our datums are. 3D comparison, even built in with a histogram. Going further down, 2D comparison, and now it's going to show our custom view if we wanted to add that too. If we don't need something, we can always just delete it right out, or we can add it right back in just by dragging it right over into our reports. And then our first result. So all of the 3Ds and 2D comparisons from our first results, telling us where our values are, if it's out of tolerance, where it might be out of tolerance, and again, showing our histograms. So just in conclusion, what can get out of Control X? Well, we are able to do various types of inspections, CAD awareness, and alignments based off of that CAD data. We can run routine inspection results, needing to just batch off something. We can import in a bunch of scans, run the same results multiple times, and then communicate this by making our customized reports. Yeah, so with that, if there's any questions, if not, we can move over to the final Q&A, kind of just the open-end part.
Yeah, we'll probably save the questions for the end and move on to Sean Parker.
Thanks, guys. So I know we're running up against time here. I'm going to make this extremely quick. I'm glad that I was able to get both of the other two presenters a little bit more time to kind of work through their applications, especially Matt's, because quality control is the primary application for 3D scanning or any kind of non-contact metrology. What I'm going to talk about today really briefly is some applications for reverse engineering. We make a product called Geomagic Design X, which I don't think I'm going to have enough time to show today, and that's totally fine. There's plenty of videos that you can find online to kind of go over some of the main features of that software. But when I'm approached by somebody that wants to do some reverse engineering, one of the first questions that I always ask them is, what type of model are they actually looking for, and why are they doing reverse engineering in the first place? And it usually gets broken down into one of two categories. It's either going to be as built modeling or as designed, or what we call design intent modeling. And just to kind of highlight the differences between those two, I figured the easiest thing to do is just show you some case studies and some applications that we've done in the past that highlight some of the reasons that you would choose one versus the other. If I do have some time, we'll kind of see what time it is when we end this here. I might show you a couple things in Design X that can help facilitate one path or the other. But really quickly, just to talk about the differences here, we'll start with as-built modeling examples. And so as-built is going to be something where the accuracy of the CAD data that I get out of my reverse engineering solution is going to be paramount, right? For certain things, especially in the automotive application here, specifically like this Formula One car, the reason that they needed CAD from this system was to generate a FEA-worthy or finite element analysis. There was a virtual wind tunnel model, essentially, of the as-built model of the car. Of course, these guys had CAD models of their vehicle, but when you make something, it may not exactly conform to the perfect CAD file that you had designed in the first place. So what happened was the company ended up 3D scanning the majority of their car. They actually only scanned the most of the half of their car so that they can kind of just copy the work, similar to what Jeff did earlier, and were able to transition this into the solid body that we got out of the system here into an FEA-worthy model, and then they were able to do some kind of virtual wind tunnels there. Another application in the automotive industry is simulation for vehicles' wheel travel and suspension. So we did some very high accuracy modeling of the inner fender well of this vehicle, and then also some feature modeling of the suspension and braking components to make sure that not only did a new aftermarket wheel and tire package fit onto the existing hub and over around the suspension components, but also inside of the wheel well here. Something else was something that we see all the time, where a existing vehicle is scanned to get the overall shape contours of the sheet metal of the part, so that we can go develop new aftermarket components for that. For example, in this case, this is a Porsche GT3 that we built a wide body kit for, or not we, but one of our customers built a wide body kit for it. So it just needed to fit very, very flush to the exterior surface of that vehicle. Something that you may have seen before, we've got this video on YouTube. It's got a couple million views, or I can't see how many million, or some amount of views here. was a project that we did with Jay Leno in an Owen magnetic vehicle. This is a concourse ready vehicle. It's actually one of the first hybrid power plant vehicles. Obviously not a very popular car these days, but this Owen magnetic, I think, was from about 1912. And had a corroded, rusting water jacket for the motor. And when we first gave the team at Jay Leno's Garage a early edit of the file, they came back to us and they said that this file was too CAD perfect. Like we had actually done too good of a job reverse engineering it. And they requested that the letters that we kind of modeled on the side of this water jacket, or I think it was a coolant sleeve here, essentially they requested that they wanted them to be imperfect because this was a hand laid casting pattern back in 1912 or so. And obviously none of those things are going to be laser straight. So we took it back and we made the file that we generated for these guys more accurate to the original scan so that it was a more accurate part to what that intended to look like in the first place. We see this quite regularly where a lot of our customers like to do floor mats or build new things to fit inside of existing shapes. So we'll scan a wheel well, and an Artec EVA or some of those other handheld scanners are ideal for that application. And then use that as a template to design new parts inside of. Same thing with aftermarket exhaust systems, for example. And there's a lot of other applications out there beyond automotive. We've done a lot of scanning with LiDAR scanners, the long range scanners that Ian mentioned earlier in the call today, where we can document as built portions of plants or facilities to make sure that new equipment that we're putting into that area is going to fit before we attempt to do it in real life. And the complexity of what DesignX can handle is staggering. This is millions of points in a point cloud, maybe hundreds of millions of points in a point cloud. This was definitely several man days worth of work, but we've documented an entire manufacturing facility here with very, very high detail to make sure that we know exactly what's there and what we're trying to fit into that space is going to fit. Similar to that, we've been able to do LiDAR scanning of the interior tunnels. We've just modeled, or not really even modeled what's there. We didn't actually do any scan to CAD surfacing. We just basically thickened what was there so that we could use that in a 3D printing scenario. Same thing with aerospace. This is a very high accuracy CAD model for, I believe this was another FEA application, and also for maintenance. Skip over to my next slide here. This is a great application for another kind of FEA or simulation application. We worked on a project with, it was a Stratus Aerospace, I think, and it was the Red Bull project where Felix Baumgartner jumped out of the capsule. We had to make sure that that suit that he wore would fit inside of the capsule, and they actually also scanned Felix in the suit so that they could get some aerodynamic data to do some virtual wind tunnel testing in there as well. And I don't want to go through too many more of these because I know that I am a little bit short on time here. Went through some with packaging, with some titled this wrong here, but this is a historical preservation and 3D printing application as well. And the highlights for as-built modeling, you can see some of the kind of history that we have here, some of the commonalities in some of those case studies, simulation and documentation of what's there, never with the need to modify or edit drastically the part that was 3D scanned. So if you want to just be able to put a new part inside of an existing space or fit something new onto an existing object, as-built modeling is perfect for it. It's very highly accurate to the scan data. It can even be automated in the case of what we see here and in the Felix Baumgartner case, where just shrink wrap surfaces are applied to the scan data and to convert it from either a point cloud or a mesh format into a CAD format. As a result of that, though, of course, the counterpoint is that the data does have to be very complete. It also has to be very high quality. So to contrast the as-built modeling applications, we'll go into some applications for design intent modeling. These are usually things where we need to make modifications to that model, and more importantly, maybe make those modifications in a software that's not ours. So one of the competing points, or one of the major points of DesignX, is the ability that it has to not just extract modeling history and features from a scanned file, but also transition or send those files downstream into some other CAD systems, for example, SolidWorks, and rebuild those models there parametrically so that the end result is essentially a native SolidWorks part that looks like you had designed it from scratch. So from this case, we were able to take a CT scan of a race car motor, do a full parametric reverse engineering of that so that the surfaces were as clean as possible, but also dimensionally accurate so that obviously other assembled components would fit into those ports and into the cylinder bores, that sort of thing. And be able to be edited once this was transitioned into some other software like SolidWorks. Similarly here with a wheel, obviously, if we want to be able to scale this up or add a different bolt pattern to it, some modification to the CAD file that deviates beyond where the original scan data showed us that object looked like will allow us to do that. Again, in some of the BIM sim applications, this bridge was something that had been in service for quite a while, and we needed to do some simulation analysis for it. So a little bit of deviation versus the scan data was okay. We wanted to make sure that all of these beams were laser straight. They were exact nominal beams. And of course, in some of the, taking this back to the conversation that Ian started earlier about accuracy versus resolution, these scanners that are long range scanners are accurate to within a couple of millimeters. So if we see some deviations up to that point, a couple of millimeters really isn't much in the grand scheme of things on something the size of a railroad bridge. So we don't know necessarily if the part is bad if it's out by a couple of millimeters, or if it's just simply the scan data is not reliable to that level of fidelity to the original object. So deviating beyond that so that we have nice, clean, perfectly straight lines, good extruded shapes and stuff like that is generally acceptable in this application. Again, some more automotive applications here. If we have historic parts that are no longer in production that we want to manufacture ourselves, possibly by 3D printing, reverse engineering, creating a nice clean file that you can see on the right hand side here is always more desirable than getting a as-built condition. You can see the kind of junky part that was used as the scan data template here. We don't want our recreated part to match that exactly. We want it to be more clean, easily manufacturable, and have more prismatic surfaces in many cases. Tool and die industries use this quite a bit for, again, automotive applications. And again, just to kind of summarize the design intent applications here, we're going to be able to deviate from the part. So if we have incomplete or poor quality scan data, as you can see in the image here, that's not going to be a limiting factor for us. Our model quality is going to be independent of the scan data quality, and it allows us to use our own design intent knowledge to rebuild a model more like it was probably originally designed to look like a long time ago. Of course, this is going to be generally for parts that are either no longer being produced or something that we maybe want to make some modifications to. So dimensional integrity is going to be a little bit more important to us maybe than accuracy to the scan data. Of course, if that part has been broken, that's an even more kind of pressing need for more of this style of reverse engineering.
So here is my contact info. If anyone can't stick around and they want to reach out directly to me, send me an email, call me, ask me whatever questions you want. I can be in a go-to-meeting with you in a second and fire up a scanner or show you whatever you're interested in. So no question too small. Go ahead and reach out to me if you can't stick around. All right, so we're going to go ahead and end it there. Thank you all so much, and we'll keep you updated on following webinars throughout the summer. Cheers.